You can hear me? You're able to listen? You may want to just choose one. Okay, so today we're just going to complete the discussion that we are doing on Bayes network learning. I'll sort of remind you what we did towards the end of last class, which is assessing the parameters of a Bayes network. If its topology has already been given, all we need to do is just do the parameters, and then basically you found that probably you were kind of underwhelmed by the fact that it really did pretty much what you expected it to do, just put ratios to compute the CPCs. Okay, and then we will basically go from there to actually say that what we just did was understand how naive Bayes classifier works. And naive Bayes classifier is one of these go-to first ideas in machine learning, just like logistic regression. In fact, back in 2006 or 8 or something, and Google used to still do its faculty summits. I remember one of them, and Peter Norvig, who is the second author of the co-author of your textbook, as well as the research director at Google, was asked, so what does Google do for its machine learning? And he said, naive Bayes classifier. So you can just use it for anything, and you know, it would be actually hard to beat it in many cases. Of course, the newer stuff like neural networks and logistic regression actually in some cases got better. But obviously, neural networks, SVMs, gradient boosting, these sorts of things work well too. But if you understand this, you know, you basically are in very good shape. And then we use that to go into learning network topology as well as learning using big data, which kind of gets us to expectation maximization idea. And that's where the technical discussion will stop, and I'll probably spend like the last 10 minutes or so sort of summarizing what we did, okay, as well as going over some of your reflections. Okay, so, and then as I said, the final exam has two parts. Part one, of course, is going to be a take home that I will be releasing, and it will be due on Monday. And part two would be a true-false questionnaire on the Blackboard, and that's where I get all my loopiness out of my system, asking random questions that you should be able to understand if you went through the entire semester. There are 50 such questions, 50, and so we are thinking of two possibilities. So since you came on early enough, I'll give you a chance to vote on this. Possibility one is it will be a time test. Okay, everything is open book because we can't check what you're doing at home. Okay, it will depend on your honor code that you're not going to talk to other people, but you're allowed to look at the notes from the class, in answering it. And try not to use just Google. Try to understand what you're doing. Again, it's basically once I allow take home, I'm assuming that I can depend on the academic integrity. Okay, so for the take home, of course, the written one, it gives you the full time. You can spend how much amount of time you want between the time it is given and the time it is due. For the true false, I was originally considering it as a time test. It's like the Band-Aid, just get it out, done, and in half an hour or 1 hour. So for example, for 50 questions, I was thinking maybe 1 hour. And so you start, and then you randomly click true and false, and you realize that if you given so it turns out that you can skip a question, and in which case it doesn't give you either positive or negative marks. But if you give a wrong answer, you get a half negative point. And if you get the right answer, you get 1 full point. And since I can't stop you from doing discriminative learning, because I'm not asking you to give me any justifications for your answer, so I think it's reasonable for me to figure out whether you guessed or not. In general, if you are more than half sure about the answer, you are better off giving the answer. If you are less than half sure, then don't do it. Although you can do the Seinfeld, George Costanza thing and say, if every instinct you have is wrong, then the opposite of it must be right. In which case, whatever you thought was possibly right, just do the opposite and you'll be fine. But here's my question. So if I do this 1 hour, then essentially everybody will just be done. When you get to start anytime you want because it's on Blackboard, but then from there it will be 1 hour. Okay, that's the time test. We could also just say no time limit. And then I'll give you in the beginning, and then it will be due probably a little more, like probably the whole weekend or something. But if I do that, you understand that you're going to spend a lot of time on this stuff. Okay? And you don't yell at me, you get to basically do the Band-Aid thing and be done within 1 hour, or just do this for the entire week, entire weekend. Okay, so how many people want timed true-false test? Okay. Okay. How many people want untimed true-false test? So it looks like untimed is winning the day. So we'll do that. Okay. So again, remember that those people who wanted timed true-false test, do it in time. In 15 minutes.
Is there a way to compare an answer, like true and false, and we decide, oh, I don't really know that. Is there a way to say an A or something?
No, if you don't answer it, then basically that's fine.
Or where you answer it, but then you said, oh, I don't really know that.
Oh, the clearing after you click,
Yeah.
I don't know. Is that possible, Prashant? No. So don't click. Yeah. Okay, so that's basically what we are going to do. So I'll go forward now. So remember that we actually did maximum likelihood-based parameter learning for Bayes networks after having started from Bayesian learning. And we actually noticed that the way you did it, the steps involved in Bayes network parameter learning, essentially, let me go there first. These are the steps involved. So you first write down the expression for the likelihood of the data as a function of the parameters. That's what you did when you did theta power n, k, and 1 minus theta power n minus k for the first example. Okay? So you write the likelihood as a function of the parameters. Okay? And then you write down the log likelihood. You take the log of it. And then you take the derivative of the log likelihood with respect to each of the parameters. If you have multiple parameters, you have to do multiple, basically you have to do partial derivatives. In the first example that we looked at in the last class, we had a single parameter. So we just did the single parameter differentiation. The second example, we had partial derivatives. Okay? So you essentially compute the partial derivatives and then equate them to 0. This is what you try to do, okay, to find the local minimum. Okay, in particular, actually, in the context of likelihood, you don't care about minimum, you care about maximum. But the same calculus comes to the rescue, right? At the minimum as well as maximum, the derivative is 0. Okay, so you basically set the derivative equal to 0. In fact, to be sure, in the steps that we did previously, we have to make sure that the double derivative test shows that what we found is not a minimum but a maximum. But we just went ahead and said, yeah, I'm sure it is just a maximum, and then did check. Okay, but essentially you are supposed to do that too. But most importantly, if the derivatives are set to 0, then you'll get a bunch of expressions. Now, in many cases, in the two cases that we looked at, you were like luckiest people on earth because you could just solve those simultaneous equations and figure out what the point at which the minimum exists. You should be able to understand that you should have been, if it was possible, you could have done this for neural networks too. Essentially, this is the way you compute minima anyway. The reason you couldn't do it in neural networks, and you also won't be able to do it in most cases, most other cases in probabilistic learning or Bayesian learning, is these equations that you get for the derivatives. When you set the derivative equal to 0, you're getting a bunch of equations. These equations could be nonlinear, and they will be simultaneous. Solving simultaneous nonlinear equations, and if you have a billion parameters, then you have billion nonlinear simultaneous equations. You see what I'm saying? Which is why, in the most general case, what you really will have to do is to do gradient ascent. A gradient descent. Descent is what you do to get to minimum. Gradient ascent is what you do to get to maximum. Okay, it's the same idea, except for the special case of completely specified Bayes networks, for the special case of completely specified Bayes networks, where the topology has been given to you, and the training data basically tells you the values for each of the variables. That's what we wound up having in our case. For that special case, your life becomes extremely simple. Essentially, the parameters are just ratios. Okay, so it's important to understand that essentially there are two ways in which this step can become very complex. In fact, to just let you know, there are two places. In one place today, towards the end, we'll talk about what happens if you have incomplete data. That means I gave you the parameter, I gave you the topology, but the training data basically didn't give you some values of some of the variables. When you do that, essentially it turns out that the likelihood is no longer a product. You have to marginalize, because of which there is no simple way to essentially equate the derivatives to 0 and find the parameter values. So in that case, actually you do gradient descent. And in fact, as I mentioned in the very first slide, expectation maximization can be seen as a customized way of doing gradient descent. Okay, it's actually a gradient descent, but for probabilistic distributions, there is a cute way in which you can make big steps instead of small steps that gradient descent has to be made normally. That's something that you want to be able to understand. But there was another name that I mentioned during the course called Markov networks, or Markov random fields, which are basically sort of a competing idea for representing probability distributions in a graphical way. Okay, and it turns out that if you go with them, there, even in the simplest case, even in the case where you're given the full network topology and you're given the full data with all the variables, even in the simplest case, you can't solve the derivatives equal to 0. You see what I'm saying? And so in there, you actually still do gradient descent. The only difference is, so it's kind of useful to understand how finding maximum and minimum can become hard. Okay? The simplest case, you will set up the partial derivatives and you set them equal to 0 and you're able to solve for the point where the minimum occurs. That's the simplest case. This is the stuff that you did in calculus 1. And you felt, I'm very good at finding minimas. Okay? And then the next simplest case is you can't solve these equations, so you have to make small steps to do gradient ascent or gradient descent, depending on whether you want minimum or maximum. But at least you know that the function is convex or concave. Do you understand what I'm saying? In that case, you know that if you keep making small steps, at least you will go to the global minimum. That is what happens when you have Markov networks with complete parameters. It is still an easy problem. It's not as easy as solving the equations directly, but it turns out that likelihood would be a concave function, and so you can actually just ascend to the top. And you don't have to worry that maybe there's some other top lurking somewhere else. And the third most general case is you do the gradient ascent or descent, but there are no guarantees whatsoever that there's only one minimum or maximum. So the function is not convex or concave, which is what we wound up doing in neural networks. It's also what happens in expectation maximization, where you have incomplete data either for Bayes networks or for Markov networks. Okay, so again the same calculus, but it becomes harder depending on what sort of functional properties you have. Okay, so that's what you want to keep in mind. And so rather than be very underwhelmed by the fact that you were able to solve these things, is this all Bayes network learning is, realize that this is pretty much the only time you will be able to solve these equations. So in this case, notice that you are able to set partial derivatives, okay, and then set them equal to 0 and you are able to solve them. Had they been nonlinear equations, you wouldn't know how to solve them. Do you see what I'm saying? Okay. Not only that, there is another very interesting thing about it, which I mentioned in that slide, unentangled, which means non-simultaneous. Notice that the equation for dou L by dou theta only has thetas. The one for theta 1 only has theta 1. The one for theta 2 only has theta 2. If you have to deal with simultaneous equations over x, y, and z, suppose I say solve for x, y, and z, where the first equation is 3x plus 1 equal to 2. The second equation is 3y minus 2 equal to 3. And the third equation is 3c plus 4 equal to 7. Those are the good simultaneous equations. Because you don't, each of those equations just directly gives you a value of a parameter. It's when they become, when the parameters become entangled, that in the single equation multiple parameters will come. That's when you become a truly simultaneous equation. Then you may or may not be able to solve the simultaneous equation in closed form when you do gradients. Okay, this is just math lesson, but math is very important in understanding what happens there. Okay, so if you remember this guy, I actually played it a little bit. Previously it used to be 0.1, I just made it 0.25 and 0.5. The entire questions that I asked would still have been asked again with this. But the difference is, if you were to use this and I had this data, what do you think this MLE expression would have given as the parameter? Because what I need to find out is, what is the probability of heads, which is theta. I need to find out what that theta is. Right? So theta essentially would be the total number of examples in the denominator by the number of examples which has heads. Right? Okay, so if you count this, essentially there are 1, 2, 3 heads, and the total number of examples are 12. 3 by 12, 0.25. That's what you will get. Okay, whether you like it or not. So for example, I show you this other example. In fact, instead of this HTT, imagine actually you had an example HHH. The first 3 process gave you 3 heads. What would MLE say?
1.
Probability of heads is 1. You really believe it? That was that XKCD cartoon beforehand, if you understood what they were saying. You see what I'm saying? I mean, it's nice to be able to teach a course where every concept there is an XKCD cartoon. Right? So basically, you don't believe it. Just because I had 3 heads, you don't believe it. Why? Because you have a prior. You really believe that the points are likely to be fake. And you need to give me really lots of examples to make me convinced that, to convince me that in fact it's an unfair point. So the difference between this and imagine instead of 3 heads, I gave you 15 million heads. If you still say, I think it could be still a fair coin, because remember, probabilistically speaking, is the probability of getting 15 million heads, one after other, is that 0? For a fair coin, is it 0? No. But you no longer want to say, none of you hopefully would say, oh, 15 million heads, I'm sure the next 30 million would be tails. That would require some level of optimism that makes no sense in the world. Okay, so in essence, your prior is overridden by the data. Okay, this is what your intuitions are. But realize that if you just use MLE, which is what we're doing here, you do have to deal with what happens when essentially you have small number of examples. And the parameters that you would learn would be fitting to the few examples. And since the priors are extremely important exactly when you have small amount of data. When there's a large amount of data, saying I still have my prior is exactly when you should say you are prejudiced. Okay? So how many ever nice dogs you see, you think dogs bite. Okay, if you see 15 million dogs, you know, I'm sure the next 30 million are going to bite. Let me stay away from the dogs. Then you are prejudiced. Okay, if you thought that dogs normally bite and you saw one dog that didn't bite and you don't want to change your mind, that's okay. Okay, because your prior still hasn't been overridden by the data. Okay, so that's what you want to keep in mind, and this will take us. So again, this idea that we're talking about, the MLE-based parameter computation for topologies, works for any base network. Any base network. It doesn't have to be singly connected, it doesn't have to be doubly connected, it can be any random base network. It will work. And the same idea. In fact, the only requirement is that the CPTs are tabular. The CPT means conditional probability tables are tabular. So you're actually writing each table. The moment you start having parameterized CPTs, things will start getting connected. And that's a harder problem. Okay? But the most obvious thing you can think of, make the network extremely crazy, but all the CPTs are tabular. You will just be able to answer any arbitrary question. So in this particular kind of network, remember this your own network, right? Burglary, earthquake, alarm, John calls, Mary calls, and I get the data which will be like this. The training data would be on one particular day, burglary happened, earthquake happened, alarm didn't go off, John called, Mary didn't call. Some other day, burglary didn't happen, earthquake didn't happen, alarm went off, John didn't call, Mary called. Notice that each of the examples are giving values for each of the variables. That's why it's called complete data. Complete data. Okay? Now, so if I arbitrarily want, let's say, the probability of John calling given alarm going off, that's the problem. That's one of the parameters I need to specify this network, right? How would I compute it? I just take in the bottom number of data items where alarm is true, and number of those where John actually called. Obvious stuff. This is what you would have done if I didn't drag you through all the calculus. This is exactly what you would have done. What you now know is what you would have done anyway is actually allowed by MLE, the maximum likelihood estimation. You guys understand this, right? Okay. Now, if you do this, there is a very nice idea, basically, as I said, naive Bayes classifier, which essentially says, okay, I just give you data like this. If you look at the textbook, you see that machine learning is all about figuring out whether Stuart Russell will wait for a table at a restaurant or not, because that's the example that he uses. Okay, so here are all the examples. Different examples where is there an alternative for the restaurant? Is there a bar? Is it Friday, etc., etc. And all of these are the features. Some of them are non-Boolean features. Okay, for all of them, you want, in the end, did you know in the training data whether Stuart Russell waited for a table? Given that you have nothing else to do, you want to find a pattern behind Stuart Russell's restaurant waiting habits. But if you can figure this out, you can think of this, and if you don't care about Stuart's restaurant habits, you can think of this as spam mails. You can think of this as credit card, fraudulent credit card transactions. So for example, the features might be how much money is being asked by the credit card transaction. Is it being done from the place where the person normally lives? Is it for electronics? Is it for this? Is it for that? And there's a bunch of features, and in the end, you happen to know whether it's a fraudulent transaction or not. That's the training data. Given that you want to learn a pattern which will, given a new transaction, you want to see, should I allow this transaction to go forward or not? This is exactly what's happening when, if you ever do, credit card transactions, especially to foreign countries, right? The visa thing comes and it circle, and it says, okay, we allow you. And sometimes they'll call you right away and say, no, somebody is trying to buy humongous amounts of, whatever, contraband items in Algeria. Are you sure? Is that what you really want to buy? And if you happen to be in Algeria and you wanted to get contraband items, you say, yeah, that's me, all right. And then they will. Okay? So that's the same kind of a problem. Okay? It's basically classification. This is yet another classification learning problem. The only difference is you have features, hand-coded features. And clearly, that's the only thing you can do in most normal classification problems. You are thinking of classification in the context of cats and dog pictures. There, the input is pretty clear. All pictures have pixels and their, intensities. That's it. But for a credit card transaction, there is no picture that you can give. You have to decide what are possibly relevant features. It's okay to put a whole bunch of features. If some of them are irrelevant, the machine learning algorithm will figure out that they're irrelevant. But the rest, you do have to put the features in. That's how essentially in industry, people kept asking what happens actually in industry in machine learning. In industry in machine learning, you say, oh my God, we want to use neural networks. What the heck do we want with neural networks? But let's just make up our own features and use logistic regression, have an naive-based classifier. But say we are still interested in neural networks, because that seems to be the big way. Okay? You do use neural networks, for example, when you have input complete scenarios, where, for example, anything about an image just comes from the picture of the pixel values of the image. Anything about a voice signal comes from the voice intensities. But everything else that you can think of, whether Russell would wait at a restaurant, whether a particular credit card transaction is fraudulent, whether somebody will buy a particular book so that Amazon can recommend it to you, whether a lot of people want to know recommendation system. That's a recommendation system that we just going to talk about. Recommendation systems are all essentially feature-based supervised learning algorithms. Okay, so normally you would have done this and then done the neural networks. We went the opposite way. Neural networks, we basically assume that there is a universe of all the features that are potentially ever relevant, which are these pixel values. And nothing in the picture. I mean, if you want to say something about the picture, it has to be connected to the pixel values, because that's the same thing you're doing. Whereas if I ask you, if you are like a bank employee and say, I think this is a fraudulent transaction, I say, tell me why, they can't show you a picture. They will show some of these features and say, notice that this guy is normally in Tempe and is hanging around in Algeria today, buying up all the electronics. You see what I'm saying? Okay. So that's the more reasonable machine learning algorithms that you have to deal with, and an answer to that, of course, is naive-based classifier, as are many other ones. But the one problem here is, if I want to just use my Bayes network algorithm that I just gave you earlier, I have complete data, right? Just like these columns are like burglary, earthquake, John calls, Mary calls, alarm. Those are the columns. Okay, so I have complete data. So I'm ready to start taking ratios. The only question is, I need the Bayes network topology. So you need to tell me how these variables, these probabilistic variables, are connected to each other in a Bayes network. Normally that involves learning the topology of the network. We will talk about how to learn the topology of the network in a minute. But the simplest idea is to say, look, don't give me a topology, I have one already. Okay? And that's where I basically like to think of it as Jean Harlow is this Hollywood star who apparently once said, obviously in half jest, to her boyfriend, that whatever you get me for Christmas, don't get me a book. I have a book. Okay? I don't even know whether you get this. But I guess you guys no longer read books, so you won't see the point. But what naive-based classifier is saying is, Don't give me a topology. I already know what the topology is going to be. Whether it's right or wrong, that's the topology I use. What is the topology naive-Bayes classifier uses? It says class, variable, two attributes. That's it. So now, this is a classification problem. So I have a class variable. This is whether or not you will wait, whether or not this is a fraudulent transaction. So remember when we were talking about discriminative versus generative models, I talked about x's, x1 to x10, and y1 to y7, let's say. And I said these y's are the class variables, these x's are the input variables. So these are the attributes are the x's, and the column, whether or not cursor is waiting, is the y. Okay, and you just arbitrarily assume in naive-Bayes classifier that the class causes the attributes. Do you see what I'm saying? This is just, you arbitrarily just made this assumption. There is no real reason why it should work. But when I give you a whole bunch of points on a plane, and I say, fit a car, what do? Did I tell you there's going to be a line there? No. You like lines. You try a line. It's a bias. So similarly, instead of looking for what is the best network, you say, what the heck, I'm just going to use this network where class causes all the attributes. Do people get this? If you get this, you now realize that this is just a special case of what we looked at already. So you have the complete data, you didn't have the topology, but your algorithm just assumes the topology is the same all the time. Class variable causes the attributes. So now you're going back to the previous slide. So then, if I have a network like this, what do I need to specify this network? I need the prior on will wait. I need the conditional probability of alternative given will wait, bar, given will wait, estimate time, given will wait, and so on. Okay, the only thing that's somewhat different from what you have seen until now is some of these variables, while discrete, are not Boolean. Will wait is yes or no, it's a Boolean variable. Okay, however, alternative is also a yes or no variable. Bar is also a yes or no variable. But look at something like estimated time. It's not a yes or no variable. It's between 0 to 10 minutes, half an hour to 60 minutes, or more than 60 minutes. It's a three-valued variable. You see that? But it doesn't make any difference. In fact, it's just a small extension, for the expressiveness. And in fact, Bayes networks just work for discrete variables with multiple values, as well as continuous variables. We don't talk about continuous variables because we hate integration science in this class, but it will work for that too. Okay. So do people think now that they understand any Bayes classifier? Okay. This is basically, we did a bigger thing and we said, now